So before we solve this fourth exercise, which is optional, of course, but that's also because it's rather special, I wanted to make sure that you understand the setting well. Here, if you look at this baseline, you see that these two sections are denoted with D or 1 minus D respectively. So it's quite obvious that this value of D, you see here, 0 lower than D lower than 1, it's like it's a so-called portion. I know I call it a portion. So it's something, it means that the fraction of this segment here of the whole line is D. Like, for example, if D equals 1/3, it means that this is 1/3 of the whole baseline AB, and then 1 minus D, of course, is then 2/3, and then this section is 2/3 of the whole line AB. So it's quite simple, but you must understand it. So it means that the blue line coming, that's arriving from here, divides this baseline AB with a ratio of D by 1 minus D. In this example, it would be 1/3 in relation to 2/3. You could also say if you bring this to lowest numbers, it's to whole numbers, it's like 1 in relation to 2, because you could say this section is then twice as long as this one. If this is 1/3 of the whole and this is 2/3 of the whole, then this one is twice as long as this one. So that's an easy task, really, but some people are in the German courses are often a little irritated by this setting. So now we are asked to use the principle of closed vector chain, which is something rather special, to prove that the blue and the red line intersect each other by an unknown ratio r, which is but the same, okay? Which means not the same as D by 1 minus D, but it's in this sentence is meant as follows. It means that the fraction of this longer section here, blue, compared with the shorter one, is the same fraction, the same ratio, okay, as here the longer one of the red sections with relation to the shorter one of the red. So that's what it means. But if you look here, you might quite clearly see that probably this intersection ratio R is not the same as the one above here, which I didn't even give a name. Yeah, so I think it should be clear. Here's a hint. The hint is use these base lines, which is quite obvious, as a basis of R2. The whole situation is, of course, a two-dimensional setting. So we would quite surely need exactly two vectors as a base of this vector space. One is then chosen to be AB vector, and the other the AD vector, which is vertically. So this would even be Cartesian situation if you want, but we don't necessarily need unit vectors to this end. Okay, so that's the setting. And now the idea is, just to talk a little bit about the principle of closed vector chain. This is nothing really new. You remember the definition of linear dependence or also linear independence, which is quite the opposite of each other. So 3 or more or any number of vectors are linearly dependent. This is equivalent to the proposition that there exists a closed vector chain like this, which is nothing else than a linear combination of these vectors using all of them, equal to the zero vector. So, you know, this is why it's called a closed vector chain, because this is like a round trip again, done or performed by the use of all these vectors. Now, but it's important, if this is only possible, or no, let me say it differently. If this is possible without setting all these scaling factors, C1, 2, 3, and so on, equal to 0. In other words, it means that you have a visible closed vector chain, which is really, you could visualize it like, for example, like a triangle built by the use of vectors. So the difference to linear independence is if you make the same, if you do the same for proving that a set of vectors are linearly independent, it will turn out that this kind of closed vector chain is just formally just possible by setting all the scaling factors equal to 0, which means in the end that it's not even visible. So, and clearly, more clearly, it means that if your vectors are linearly independent, it's just not possible to construct a real closed vector chain. So I think you got this, okay? Now, if this is the case, linear dependence, then it's also equivalent to saying that any of these A vectors is a linear combination of all the others. Okay, so this is valid for all I. This is what I also told you last time when finalizing the first exercise, which came a little short. So anyway, now the solution to this interesting problem. We want to find out the intersection ratio R, which is exactly the ratio by which the red and blue lines intersect each other. So for more clarity, I use the following symbols. Again, this D in green color here, I told you what it is. The example was if it's 1/3, then this one is 2/3. So this is just the way that the baseline is divided by this point, which I call S here, okay? So on the other hand, we want to know about this portion. All these are portions, right? So D, X, and Y are portions. I could also color this in green, okay, like this. But probably, and what we should show firstly is that X and Y are the same. That's one thing, because if X is equal to Y, it means that the blue and red line intersect each other by the same ratio. On the other hand, X and Y will quite surely not be equal to D. This is almost visible by blank eyes, okay? So, but how do we do it? If I call this one X, which should be a portion, then the other portion will be 1 minus X. This one I call Y, and the other one will be 1 minus Y. So I chose them in a way that obviously the smaller ones are called dxy, and the other, the longer ones are called 1 minus d, 1 minus x, 1 minus y. That's it. So now this is, I think it's quite, well, probably it's quite obvious.
So one question.
Yes, please.
Why is x equal to y? Why should x be equal to y?
This is one of, I show you. A good question. It's hard to see, but this is what we should prove. Okay, I don't really know why it is. We will see. Okay, but here it says construct an appropriate closed vector chain to prove that the red and blue lines intersect each other by the same ratio. That's it. Okay, the same ratio. And if this ratio R is the same for blue and red, it means in my expressed in my symbols, it means that X equals Y. Do you understand this? Or is it still not clear? I think it's not, right? Okay.
I am able to understand the ratio and things, but I am still not convinced why it is X should be equal to Y, because they have only mentioned the same ratio.
Well, now the question is where the problem lies. I admit, if you say, I don't say that this is the length of X and this is the length of Y, okay? In this case, it would be false. It's quite obvious that this line segment is shorter than this one. But I think that's not what you mean, is it? Because like I said, dx and y are portions. They are not lengths. They are like fractions, okay? You know what? I show you an example. That's the best to get oriented. The example comes after we have solved the problem. I can tell you quite exactly for the given example in the sketch, okay? It's a fact that this has a portion of 1/3 of the whole baseline, and this is 2/3. So this is twice as long as this one. That's quite a fact. If you take a ruler and you can check it, okay? And the result of our whole solution will be that the portion of this one is then exactly 1/4, and also the portion of this one is 1/4, always related to the length of the whole. Okay, so of this blue line, this this is 1/4 of it. And of this red line, this is 1/4 of it. And the remaining 3/4 are here and here. So that's a fact. And the exercise is to prove this. Okay, so if you just think momentarily, you think, oh, why is it? That's no problem, because we want to prove it. But you should, of course, you should firstly understand the concept. I hope you understand the concept. The concept is now to show that x equals y, which does not mean that these segments are the same length, but the portions are the same. Better now?
Yeah, Professor. Maybe
Okay.
as you go along the answer, I'll understand
Yeah,
more.
I think so. So it's just follow me with all these symbols. So what do? Firstly, I define the base in this. Let's say this is a two-dimensional vector space. Okay, we use vectors all along, and I say this vector from A to B, point A to point B. I call it basis vector A, and the second one from A to D. This one I call it vector B. So this is my basis in this vector space A and B. Obviously, they are linearly independent. Okay, so this is a valid basis. Anyway, now I construct a closed when I say real, I mean a visible closed vector chain using this little triangle, because this is so nice here. Yeah, it's the smallest one that I can find, and also it contains all our interesting portions, like called D, X, and Y. So I say, look here, C1 from point A to this point, then I go on with vector C2, and then I go on with vector C3, and you see that this is a closed vector chain. Perfect, okay? And the vector sum of these three is equal to the 0 vector. Now it's important to see, because these are three vectors building a triangle, it's obvious that they are linearly dependent. So it means that this equation must have a solution where I don't even need these scaling factors, you see. I don't need any additional scaling factors, because I construct my vectors in a way that it fits. So in the end, the scaling factors will be 1, 1, 1. But this means they are not all equal to 0. And back to here, it fits. Okay, it means we have a visible closed vector chain without, and so now, okay, I hope this doesn't embarrass you that I use C symbol now for these vectors and not for the scaling vectors. In our example now, this is 1 times C1 plus 1 times C2 plus 1 times C3 equals 0 vector, and all these scaling vectors are not even one of them is equal to 0. They are all equal to 1. So it's a proof also that they are linearly dependent. But this is obvious. Okay, so we just started. Now it gets interesting. Now I try to express these three vectors by our basis with consisting of vector A and B. Okay, so and now look here carefully. If C1 is this vector, so it's obvious that it points along basis vector A, but it's just a portion of D, yeah? a portion of D regarding this whole basis vector A. So I just write C1 is exactly equal to D times A. Just keep the example in your mind. Okay, it's best for you to keep this example, this numeric example in your mind. So if I say D is a portion, it means that this segment is 1/3 of the whole length here, and that's true even for this picture. So you can agree to me that C1 will be 1/3 times vector A. But it need not be 1/3. It could also be 1/4, 1/5, whatever you choose for D. Okay, so but it's a fact. Then the second vector here, where does it point? It points from here, and it's obvious that it has something to do with the direction of the blue line, which I completed also to be a vector. You see here with the blue vector arrow. So what is this blue one? What is it? It is, I must go, I must always think about it. Yeah, I must go against, if I start here, I must go against C1 from here to there, and then up the whole vector B. And then I get, in sum, I get my blue vector. You see? So this would be minus D times C1. But since C1 is, or no, let's do it differently. Minus C1 is what I need. And minus C1 is exactly minus D times vector A. Okay? So minus D times vector A, that's what I do. to go from here to here, and then I go the whole way up with plus vector b. So this is the blue vector, but the C2, which we want to express, is just a portion of the blue one, exactly speaking, the x portion. I defined it as to be a portion of x, okay? A number between 0 and 1. So that's it. That's my C2 vector expressed by the basis A, B. And finally, the third one, you see it points along the red line, but it's not the whole red line. Anyway, I will also try to express the whole red line as a vector, which is easy because I have to go down here, you see, down here and over there. So actually I go minus b and then minus a. I could also make it this, do it this way. If I go from here along vector a plus along vector b, I would get the red line in this direction. But we need the other direction, so that's why I put minus a minus b, and that's it. But then also the C3 vector is just a portion which we called y of this whole vector, so the whole thing times y. Why do I do all this? That's important to know. I do it for a quite funny reason, because I will now try to put this actual and visible and functioning closed vector chain in a form so that it looks as if it were a vector chain just using a basis vectors a and b. So that's what I do. I replace, now here, I replace this C1 by d times a vector. Here I'm going, okay? I replace this one by this black term. I just remove the brackets, you see, remove the parentheses. You see, next term is x times minus d times vector a, this one, and then plus x times vector b, I'm here. And then finally plus the third vector, which is removing the parentheses, y times minus a. Where is it? Here. You see it here, minus y times a, and then also minus y times b vector. That's all I have. This is still a valid and visible closed vector chain. But now I rearrange my terms. You see, I will bring together all the terms which contain vector a, and then put this outside of the parentheses, or put all the factors inside parentheses. You see what I do? D here, then minus x times d next to it, and then also here this minus y. So this whole term multiplied by basis vector a is all we have containing a. And then concerning b vector, we have x times b vector minus y times b vector. So it's x minus y in parentheses times b vector, and still equal to zero vector. Now comes the real, yeah, you could say the funny part, which is, although this still is a true closed vector vector chain, now it looks as if it were some scaling factor times vector a plus some other scaling factor times vector b. And now we can really be sure that vectors a and b are linearly independent. They must be, because they are the basis of our vector space. So what does it mean? It means that if I construct a closed vector chain in this way, which is written here, this equation can only have the trivial solution, because it's just not possible. Just try to go a certain amount in this direction and then a certain amount in the vertical direction, and then try to arrive where you started. You will never make it. And because you will never make it, it means that the only solution to this equation is that the scaling factors are zero. Don't you think this is quite interesting? Because here it looks like, yeah, I can see it, it's a closed vector chain. And now we transformed it to be, you could say, an open vector chain, which is not solvable, except for the trivial solution. And that means, and you will see that this is really a quite convincing result in the end, this factor must be zero and this factor must be zero. So this is quite a special topic, but I think it's highly interesting. You agree with me that these two factors must be zero? So now, look here. This one is more simple, so I start with this, okay? It means that x minus y is equal to zero. And in the end, it means x is exactly equal to y, okay? And this is what we wanted to show. The intersection of red and blue lines is by same ratio, which we called R, and which is you see what it is? This ratio R is actually X in relation to 1 minus X, or even Y in relation to 1 minus Y, which is the same as we just showed. And you can see it, okay? You can see that the portion X regarding the whole blue line is the same as Y regarding the whole red line. So it's quite convincing. And then after we showed this, we can proceed to the second, I must say, yeah, I think so, 1, 2. So this actually was part I, okay. And then, but I should start, I don't know, I probably forgot it. I should say from here on, it's part 2, okay? Now, look, we have shown that X must be equal to Y. So this means from now on, we can just replace Y by X and just use one of them. So inside here, I just replace this Y by X because it's the same. And then I set this factor equal to 0. You see, D minus X times D, but then minus Y replaced by minus X equals 0. What do? Well, I don't know, yeah, I just put this in parentheses so that you see these two terms contain X, and then I can pull it out of the parentheses. So I have X times, in the parentheses stays just D plus 1, okay? So then I can easily isolate X in this equation. Next step is X times D, this is D, okay? D plus 1 equals D. And then I divide the whole thing by D plus 1. And in the end, I get that X is equal to D by D plus 1. Now, that's a fact. And by the way, also Y must be equal to D by D plus 1. What I can also do, I can build 1 minus X, just for clarity. 1 minus X is 1 minus this fraction, okay? So the 1 I can put, you see what I do? I expand the 1 to be something by something, which I can always do, okay, same by same, which equals 1, D plus 1 by D plus 1, and then I subtract X, which is D by D plus 1, just to put it in a certain simple fractional form. And then I pull these two fractions together, and I have D plus 1 in the denominator, and in the numerator, I get D plus 1 minus D. So D cancels out, it stays with 1 by D plus 1. What have I reached now? I have proven that while X is this expression, if I express it by D, okay, and the other portion, 1 minus X, is this one. So the question was about the intersection ratio R, which is defined as, you see here, X in relation to 1 minus X. Also here, now I replaced Y by X because we found that they are the same. And so this intersection ratio is, exactly speaking, and I put it in this form, that, okay, this time it's the longer divided by the shorter portion. I could also have used the inverse fraction. Anyway, then it's 1 by D plus 1 divided by D by D plus 1. So this is a double fraction where I can expand, and so that I can cross this out, and then it stays 1 in the numerator and D in the denominator. If I'm correct now, so the result for R is 1 by D, which means you could think, okay, so this is roughly speaking the same as this D intersection ratio. No, because D is a portion, and that's because this is so embarrassing. It always helps, for my taste, it always helps to use a good numeric example, and that's why I did it. And now follow me once more. If I suppose that D equals 1/3, which is quite obvious, it should be around 1/3. And then also, but I could move these lines around so that still the equations hold. But in this example, okay, I should say this should really be built from the corner, yeah, if you look exactly. So if this is 1/3 and this is 2/3, so what do I get? X, we said X is equal to D by D plus 1. So I have 1/3 here above the fraction line, and 1/3 plus 1, which is 4/3 in below the fraction line. So if I reduce this again, I get 1 by 4. And now you see, if d equals 1/3, then x equals 1/4, and also y equals 1/4. And you see this by blank eyes. By blank eyes, you can see that this makes sense, okay? Because if this is a portion of 1/3, this should be a portion of, roughly speaking, 1/4 here and also here. So this is absolutely correct, what we've done. The question is, have you really understood it? I hope. I hope at least you have a partial understanding now for what we've done. And I think the most interesting part was this trick to, well, to convert an actual closed vector chain to another one which is not possible, and then arguing that those scaling factors have to be 0. It's quite funny, I think. But just to calm you, if you think, oh, this is too hard for me to do by myself, don't care about it, because this is quite surely not a typical exam exercise. You will not have to do this in the exam. I may promise to you. Okay.